So hello everyone. So I'm Khoi. So I'm the chair of these sessions. So we're gonna start the present. The first presenter is a Minh Nguyen. So application of the spherical format, the linkage mechanism, and the fin-lay structure design for fish robots. Please welcome.
Good afternoon, everyone. My name is Khoi. I'm coming from the DC lab from Hong City. So today I will represent the application of spherical for linkage mechanism in fin-lay structure design for fish robot. So what is a fish robot? Why we have to build a fish robot? Because we in military we have to track the enemies using by radar and make the enemy cannot track us. So we cannot use some mechanism that have a very noisy machines. So that's why we build a fixed robot for the marine in Vietnam. It's a project serve for the marine in Vietnam. So a fixed robot we use utilizing the NPF, or also named is the maiden paraffin that you can see it has So it has two fins on the two hands, and the fin membranes are composed of lymphoid and continuous materials, or you can know as a rubber, a normal rubber. And the application of this is a spherical force linkage. The scope of the research is that we have to analyze the kinematic of the mechanism and calculation of the torque transmission efficiency using the power method, and this will propose a method for forming a spatial for linkage mechanism. And when we move to the methodology, when we build a fork analysis of the fin membranes, we have to simulate the fin membranes using the CFD method, aiming to dismantle the force interaction between the fluid and the fin membranes. And according to reference 1 and 2, we can completely construct the mathematical of the model of the fin membrane using the rule surface method as follows. You can see on the screen that the C1U is according to the S, Y, and Z coordinate. The C12 in the blue line, you can see over here, this will have the radius R. This will have the radius R, and C2U is the formula that according to S, Y, Z, and this determine the red line. And the rule surface of the mirrors is that's the color between here, the surface between the two lines will be connected by this equation from FUV, you can see on the screen. And we put this mathematical into the MATLAB software and safely simulation to analyze the force analysis on the fin membranes. So the rule for generating the movement of each node of the fin membranes, you can see that the fin will have a sin line right here, and the angle theta of the each when it goes up and down, you can see on here this is the sin equation. And at each time of the point and the force, specific parameter value the point of the plane will moving according to the reference 3. So when we move to the simulation, when we have the maximum parameter, on the middle of the image, you can see that we have a square. We call it rim. We have a square, a square box, and on our side is the fluid, the environment that we call the tetrahedrons. The parameter of the meshing when we put into the simulation that we have the size of the fin element is according to this number. The height of the inflated element is according to this number, and the number of the layer is according to 3. So this is the testing parameter we put into the simulation. So then we move to the kinetic analysis of the spherical for linkage. Then we make this a coordinate table. We paste on the GH table for the linkage. You can see on the table on the screen right here. And according to that table, we will have the theta is the angle between the surface GOA and the BOA, and the test is the angle between the surface COD and the GOA. So we will have K1, K2, K3, and formal equation of the kinetic. You can see both here. So we have to calculate the position equation, and then we have to determine the velocity equation on the 6. Then after that, we will analyze the torque equation. It's according to this TU. So this is when we put the mathematical the field and the kinematic equation into the simulation that we have. You can see on the left hand, this is the torque. The maximum torque is right here, and this one is the minimum torque of the applied to the fin. Where the fin, the force simulation is where the fin when it's moving at the frequency at 2 Hz, and in the deep sea water it comes to 30 meters below the sea level. The scene equation I talked above is according to this line right here, and based on this we have a graph moment of the motor for balancing the applied torque with the input angle. Below is the angle we move from the 0 to 60 degrees, and the torque will become from 3 to 4.8 Newton meter. So we put it in and some controller into the real line of the physics board, and the physics will because we don't have so much time, and this presentation is a part of the big problem, so we just put into one part only. My physics board is have 18 balls on the 2 hands, and the right E9 and the left E9. So you can see it right here. The formal linkage is right here. The motor we use to control the fin is we use the DC support motor. It has a torque. It can be up to around 15 Newton per meter. So from the result right here, we only need 4.8, so it can apply. So we move to the summary of the study. Applying the linkage mechanism to the fin assembly instead of conventional transmission, and additionally the paper proposed a method for analyzing force on the fin membrane to find a motor with the torque. So we have to discuss the application of the linkage mechanism provide the flexibility in underwater operation. However, the accuracy of the mechanism heavily depends on the precision of the component and their manufacturing process. Because we build that in a workshop, and we have some error when we manufacturing, so we have some when we put the controller and algorithm into the real life, we have some disturbance into the controller, so we have to fix. And the use of the method to generate the trajectories for the point on the fin membrane and to create the operation process. You can say that how can we know the point underwater? We don't know that because we don't have any eyes on them. I mean eyes, it means sensors or something like that. Like you have to how we know the fish is moving? We don't know that. So to the algorithm we build here is to create the operation process to the fin membrane. However, this method is limited by the number of points on the fin membrane because the more point there, the larger the step size for calculation, leading to the significant combination loss and simulation runtime. Because you can see the result we build here, we have to run it about 25 to like, this make me 2 days for the computer to run rapidly. So if we have more point on it will increase the time and it costs a lot of money to build a station, a computer station to simulation that. So in the future, the paper is not on the preliminary calculation method for the required torque of the motor. It has not yet proposed a specific dynamic mathematical model for control purpose because we can know that we only stop on the step that we build a controller for control the field on the surface. We still not put the mechanism into the sea level. So it will become the future work. And the coordination between the field assembly, create the swimming pattern of the robot and controlling this mechanism, rotor, and coordinating them will be addressed by author in the future. So this is two reference I feel, and thank you for your attention. That's all. If you have any questions, please let me know.
No. When do I need to give him? So I have to finish the annual presentation, I have to give it. Okay. Can I do it later? Because this is conference, so yeah. So just put there as I just give the end of these sessions, I give to the presenter. It's okay. Do you have any questions? No. So I have a question. So basically you mimic the robot, right?
Yes.
So you will have the computation of the mathematical model, and also so you have the device for the experiment. So how fast can you move with your robot?
The speed of the robot will be moved.
Yeah.
It's about 0.1 meter per second.
So what is the real speed?
The real speed? We still don't have the real speed in that because we still is on the book on the step of building the simulation.
I mean, if you try to experiment.
Yes.
So how fast can you move?
I actually calculate about 0.1 meter per second where it's moved under the sea.
So it doesn't matter so about the height?
Yes. It's that we have to have a design value of velocity. It's about 0.1. So we have to build a controller to give in that trajectory in the design value.
Okay.
Yeah.
So when you try to swim in the deep side or just on the shallow side?
Shallow only.
Shallow side.
Yes. It's about 20 meters below the sea level. 30 meters. So we put the parameter of the 30 meter below the sea level into the simulation right here. It has the same pressure of the sea level put into onto the field and also the rack force of the sea level. We also put into it.
Okay.
Yeah.
What you said is there's a 2 hertz.
Yes.
So you want to experiment the video. I think it's quite slower than that one.
All right, because it's quite slow. Yes, this about, I don't remember exactly because we have so much things to do about this mechanism in real life. So we continue to build it in the future.
So both sides the same movement or?
It's in opposite direction.
No, it is the left side and right side.
Yes.
There's 2 sides have to robot is move
Yes.
to the weight, right?
Yes.
So it has the nice.
Oh, right,
movement,
yes.
isn't it?
Yes, we have videos, but I don't bring it in. We have simulating the 2 things. Yes, but the data is not good enough until now.
Okay.
Yeah, so I cannot say.
So you will keep studying.
Yes,
Okay.
yes, yes.
Yeah. That's good. Any other questions or comment? None at all? All right. Thank you for the nice presentation.
Okay, thank you for your attention.
Okay, so next speaker is Dan Lee. So